So now we finally get to some physics. And this is translational motion. Now, most of this section deals with motion just going back and forth along a line. And so I could draw a line, I could draw it in a vertical direction, for instance, and I can imagine there's this little dot that's moving up and down on the line. You know, it can move up this way, it can move up, keep moving up for a while, and then it could come up at here and stop, and then it could go back this way and come here, and so on. So it's moving along a line. So this is mostly, let me go ahead and draw like this. So this is mostly along a line. And so that means it's one-dimensional, because a line is one-dimensional. And then later in the chapter, it gets into projectile motion, where it has motion in 2 dimensions, where there's an x component and a y component. So for this part here, we're not going to be having to use this trigonometric stuff, because we only really have one direction. This is relating things like position and velocity and acceleration and things like this. Now, there's 3 equations that we're going to talk about here. And so, but first we're going to talk about the variables that are involved in this kind of motion. So there's these variables, and so we have, you know, I've listed some of them here. X is often used for position, or sometimes distance, or displacement, or things like that. Now, there's a distinction between this word distance and this word displacement that the book makes, but that distinction is not always made in problems that you actually see. And then you have V, it stands for velocity. And sometimes you use something like S for speed, which would be the velocity without direction. Another thing you'll sometimes see is you'll see V with a little arrow drawn over it for velocity. That's the arrow means vector, and then V without the arrow for speed. So this would be velocity and speed. And of course, I wrote here this for velocity. Here I'm writing V for speed, and all this illustrates is that you have to say, you have to pay attention to what the problem's telling you, because the letter that's used for it doesn't always necessarily mean the same thing. It means whatever it says it means in the problem. So, but in this case, we'll just stick with velocity here. And then T, of course, is time. I guess I'll go ahead and write this last. I'll just keep this in order here with acceleration. Now, usually, because these are simple problems, this is usually constant acceleration in this context, and then T is time. And there's a number of different things that you can do. Now, what I'm going to do next is I'm going to talk about these equations here, and these are equations you need to memorize, unfortunately. At least you need to memorize these 2. Now, you can get this third equation from these 2 equations by plugging one of them into another. But it's a good idea to have these equations memorized, and they put them in red in the book, and they tell you to memorize them and stuff, so that's a good plan. So I'm going to tell you what each of these equations say. So these are equations. So this is for motion along a line. All right, so I'm going to write the equation. I'm going to rewrite the equation out big, and then I'm going to write arrows that tell you, that point to each of the things in the equation. So the x minus x0 equals v0 t plus 1/2 a t squared. Well, this x here is, this is time dependent position or displacement. These words are really interchangeable. Displacement means you start out with a particular point that you consider to be your origin, and the displacement means how far you displaced from the origin. The position would mean essentially the same thing. What's your position with respect to that origin? But you could see either word used. So this x0, this is initial position. Now this word initial, what does that mean? It means when the clock starts. So this is at t equals 0. It almost always means when t equals 0. So the 0 down here means that the time is starting out 0. You think about having a stopwatch, and you say, okay, what the x0 is that's where I'm started. It's like your starting block, like if you're sprinting or something. You're at the starting block. That's your initial position right when the gun goes off, right when the stopwatch starts. That's when t equals 0, and then it starts counting up. Now these two together, x minus x0, this gives you the change in position. And I'm cluttering up my diagram here, but too bad. Change in position over time. So when this says time-dependent position, well, this says, I mean, if I wanted to, I could write this as a function. I could say this is x of t, because it's a function of time. So this is x after some time has elapsed, after however long t is, t seconds has elapsed. Then this is what the position is then. This was the initial position, so the difference between those two, the final position minus the initial position, that gives you the change in the position. That's what this is here. Okay, now the v0 is what you would expect. This is the initial velocity. Now in my example of racing, where you're starting out in the starting blocks and then the gun goes off and that's when the time starts, in that case your initial velocity is 0 because there's no, you're not moving. But it wouldn't have to be 0. I mean, you could imagine somebody running up to the starting line of the race before the race starts, and they're running up to the starting line, and then they hit the starting line just as the gun goes off. In that case, they would be starting at that same initial position, but their initial velocity would be different. So this is the initial velocity. This here is the acceleration. Now, this equation here only works if the acceleration is constant. So here, this must be constant. And then the t, of course, is time. So both of these here are time. So that's what this equation means. Now, the purpose of this video is not to work problems. That comes later, but you'll be aggravated at me if I show you all this, theory without working some sort of problem. So let me do a very simple problem here. And so the problem is this: you have a cliff and you drop something off the cliff. So say you have a rock here, and you drop it off the cliff. And you say the rock takes 5 seconds to hit the bottom how tall is the cliff? Well, how would I use this equation? Well, I know there's a t in there, so you remember what this equation was. I had x minus x0 equals v0t plus 1/2 a t squared. I know the t is going to be 5, because see, this is the 5 seconds. That's the t here. And the x minus x0 is really what I want. Now, what I could do is I can either decide that the height here, I could say the x0 is h. Say I call that h. This would be the height. So how tall is the cliff? I could call this thing h. Now, if I did this, then what would happen? Well, the x, the distance from here to here, minus the x0, so this would be 0. This height here is 0 at the bottom of the cliff, and the height at the top of the cliff is h, then x minus x0 is actually minus h. But we're not going to care about the minus sign. Now the initial velocity is 0, because we're just dropping it, so we say this is 0. We can put the 5 in there if we want to. And then the acceleration is this acceleration due to gravity, which the book uses. You may have seen this 9.8 or negative 9.8 meters per second squared. The book just uses minus 10 or 10 depending on what the direction is. So this would be plus 1/2 and then minus 10 if we use the book. And then t squared, this will be 5 and this will be squared. And so what does this come out to be? Well, this is minus h equals, that all goes away because of the 0. The 5 squared becomes a 25, the 1/2, so we get the minus comes out in front, so we get a minus 1/2 10 times 25. And so the minuses go away. They're minus on both sides, and so we get h equals, what does this come out to be? Half of 10 is 5 times 25 is 125, and the distance is going to be in meters. So that would be the answer to that. It may bother you that I put a minus sign in here. The point is, if I have the minus sign associated with the x minus x0, in other words, if I have the x0 be bigger than what the x is, then I have to have the minus sign associated with the acceleration here. Otherwise, I could flip it around and I could say the positive direction is this way and the acceleration. You just have to make the acceleration agree with the direction that you choose there. Anyway, you can think about that as much as you want. So that's that equation. And then the other equations are simpler. Well, at least this one is. They're not any more difficult. And so this v minus v0 equals a t. Well, this is clear now what this is. This is time-dependent velocity. This is the initial velocity. And initial, of course, means t equals 0. So that's the velocity when t equals 0. This is the acceleration, and we're assuming again that it's constant. It must be constant for this equation to work. And this is time. Now, a simple problem you could do, following on the last problem. So if I draw a line across here, is you could say, well, how fast was the rock going how fast was the rock traveling when it hit the bottom. Now, the how fast, this how fast here is v. The v0 was 0. So we have v here minus 0 equals a. What's the a? Well, that was minus 10. You notice I could put units in here. I could put meters per second squared. I'm not doing that. And then the time was time here. And so this would say the velocity equals minus 50. And then I'm going to put meters per second here at the end. So this is v equals this. Now what's the minus in there? It's because it's going down. That's why there's a minus there. If I wanted to just say how fast, well, I could say then that's really speed instead of velocity. And so I could say the speed is 50. The velocity is minus 50 because the minus gives you the additional information that it's going downward. But that's, it wasn't specific enough. I didn't really tell you which of those I wanted here. In any case, the velocity is minus 50 because it's going downward and the speed is 50. Okay, so then there's this one last equation here. And this is, let me scrub this off. Of course, you already know what the components of this mean. V squared equals, that's time-dependent velocity. It's the initial velocity squared plus 2 times the constant acceleration times the final position minus the initial position squared. And so this, you can get this from the other two equations if you want. And the way you would do that is you would start with this v minus v0 equals at, and you move the v0 over, so you'd have v equals v0 plus at, and then you'd square both sides, so you'd have v squared equals v0 plus at squared. And then if I want to laboriously square this, I can, and I get v0 squared plus, and now you're going to be aggravated at me, the 2v0 at plus a squared t squared. And then this part here, so I'm trying to get this equation from this equation here. What I would do then is that I would notice that if I factor out, so this is v0 squared, if I factor out this plus 2a, what's left? Well, I took out a 2a here, so I have a v0t. And then what I have over here is a 1/2 at squared. And all of this is exactly, see, it's the right-hand side of this equation here. So it's x minus x0. And so what I've gotten out of all this is exactly what I wanted. V squared equals this thing here, v0 squared plus 2a times x minus x0. And that's this equation up here. You are not going to want to do that, certainly not while you're doing the MCAT. But I just want to tell you that these two equations give you the same information. You don't need to memorize this one separately if you don't want to. I don't know. I mean, that's not too long to work out. I guess maybe you could work that out if you don't want to remember it. Oftentimes you'll see this equation down here written as v squared minus v0 squared equals 2a x minus x0, which is the same thing. You're just moving the v0 over there. Okay, so this is plenty of theory for one video, and next we'll do problems, and that will be a lot more concrete. So that will be in the next video.